Yeah, welcome. So with this lecture, we'll be moving on to the next topic, which is adversarial search. So with what we have discussed in the last class, with that, we'll be stop discussing local search techniques. Now we'll be moving on to the next topic. This is adversarial search. Okay. So first, let us try to understand what is meant by adversarial search. So in an adversarial search, there are two players. Minimum there will be two players in an adversarial search. So the player one, the player one will always tries to maximize his performance. The player one will always try to maximize his performance, or he tries to maximize his score, or whatever it may be. He tries to maximize, right? Okay. So whereas the player two, there is another player. The player two, he always tries to minimize the player one. He always tries to minimize the performance of player one, whereas player one always tries to maximize his own performance. So, in this context, how the search should proceed? That's what we are going to discuss in adversarial search. So there are two agents. So actually there it is something like two players, player one and player two. So basically, player one, he wants to win. Player two, he wants to win. So in other ways, in other words, we can say that player one want to maximize his score and player two want to maximize his score. But we are focusing the problem from player one's perspective. Okay, we are focusing the problem from the perspective of player one. So from the perspective of player one, if you see, the player one always want to maximize his score. Then instead of saying that player two want to maximize his own score, we can say that player two always want to minimize the score of player one, because when the score of player one is minimized, obviously the score of player one maximizes, right? So we are focusing, we are seeing the problem from players one's perspective, right? We are approaching the problem solving approach, we are from the players one perspective. So as a player one, we always try to maximize the performance, but at the same time we should be aware that there is an opponent who is always trying to minimize my performance. So in such a scenario, how the search or the algorithm should proceed? So that's what we are going to discuss in adversarial search. So that the name adversarial, so there is something, there is some adversarial element is there, who always tries to uh, reduce our performance. So in that environment, uh, how the algorithm should work? Okay. So we'll be trying to understand adversarial search with some games, with some game playing examples, like chess, or any other games. So there is a question like, why AI researchers study game playing? Why are we taking games and we are trying to understand? Why can't we take some real life scenario? So instead of taking real life scenarios, why are we taking games? So there is a question. So the answer is, actually, if you take any real life scenario, first of all, the real life scenario may have innumerable number of states. They may have innumerable number of states, and we may not be able to represent or specify all the states. And second, the rules may not be fixed. The rules may not be fixed. The rules may change. The rules may change. So because of this, the problem itself, we may not be able to define the problem itself in a proper way. But if you take any games, in a game like chess also, if you see, there are many states are there. So if you take a game, that doesn't mean that it does not have many states. In game also we have many states. For example, if you take a game like chess, there are so many states are there. So it is really complex. So in one sense, it is equal to the real life scenario, but the rules are fixed. But the rules are fixed, and we know the rules of the games, and we know that if this is the rule, if you apply this rule, that will happen. So like that, we have standard rules. So with standard rules, it becomes it becomes easy for the algorithm to implement, and also we can verify, the performance of the algorithm with humans or with other machines. Okay. So that is the reason why we are interested in, why AI researchers are interested in games, because games are a good reasoning problem. It is more formal. It is non-trivial. Non-trivial means it is not very obvious. So that doesn't mean that games are easy. That doesn't mean that the real world problems are tough and games are easy. No, in games are all so games basically simulate the real world scenario to some extent, right? Or to a larger extent. As the complexity of the game increases, the it becomes more non-trivial. So if you take any video game, any typical video game, initially it will be of very less complex, right? That is, it will be very trivial. First two stages you may be able to cross very quickly, but as the stage increases, as the level increases, when you go to third level or fourth level, it becomes more complex, right? Uh, so actually the games are a good approximation of what is happening in the real world, right? So it's a good reasoning problem. It's formal and it is non-trivial. And in real life also, if you see, uh, intelligence is more connected with games. Intelligence in real life also, if you see, intelligence is more connected with game. If somebody is good in intelligence, they will be good in playing certain games also, like chess, cards, right? So these games really, actually, it even improves the intelligence of individuals, because it improves the thinking capability of the individuals, right? So right, so these are some of the reason why the researchers are interested in games. Okay. And already somebody has worked on the game, and the rules were, uh, we have some concrete rules. For example, if you see the game of cards, there are different plays are available in cards, right? And for every play there is a rule, and it is a very concrete rule mathematically, right? So so just I'm trying to justify why solving the gaming problem using AI, it's not a bad idea. In fact, it's a good idea, right? So, and also whatever the results we are getting, we write an algorithm for game playing, for playing some games, and the result can be easily compared with humans and other computer programs, right? So it's not that only you are writing a program. Say already there is a program somebody has written for chess. Say let us call it as algorithm one. Now you are writing a new algorithm for chess. Let us call it as algorithm two. Now whether my algorithm is better than the existing algorithm or not, I can compare, right? And also I can compare my performance with some other humans, right? So all these are possible with the games and its existing rules. So these are the reasons why the researchers are interested in uh, solving or trying to solve AI problem through games. Okay, fine. And mostly many games are of strategical nature. Okay, many games of strategy, and, and most of the games are of strategic nature. They are not sequence. So sequence means, so when a solution will be a sequence, a solution will be a sequence if it is a single agent problem, or if it is a single agent game. If there is only one agent is involved in the game, and if the environment is deterministic, if there is only one agent and if the environment is deterministic, then the solution will be sequence. Otherwise, if there are multiple agent is there, obviously if there are more than one agent is there, one is agent one who is and the other one is agent two. If agent one and agent two are opposing each other, right? Either agent one will win or agent two will win. In that case, it becomes strategic. It becomes strategic because agent one always tries to improve his score, whereas agent two always tries to reduce the score of agent one. Right. So in a game of strategy, this is the following characteristics. The games of strategy will have the following characteristics. What are they? There will be sequences of moves to play. That is, if first agent one plays, then after that agent two will play. Once agent two plays, again agent one will play. So like that they will alternate their moves. Rules that specify possible moves, and there will be fixed rules like what are the possible moves are allowed, which moves are not allowed. All these things will be fixed. Rules that specify a payment for each move. So when you do some good move, you will get some credit. You will get some credit. Okay, and our objective is to maximize your payment. So when you make a right move, you will get some credit either in terms of point, or you will kill somebody in the opponent, or you will strike off somebody in the opponent. All these are what? It is a payment, and your objective is to maximize the payment. So if you take any game of strategy, that is, if you take any multi-agent game, then it will have all these features. There will be sequence of moves to play. There will be rules that specify the possible moves, and when you do a good move, you will be paid. That is, you will be rewarded, and the objective is to maximize your payment or the reward. And what's the difference between the games and search problems? So if you see here, search problems, in the sense we are talking about so if you see, we are talking about search problems in the sense we are talking about actually the ones with single agent. Okay, single agent problems, that is, which provides a sequence as a solution. And when you say games, we are talking about multi-agent problem, or the problems which we are working in an unpredictable environment, right? There is non-deterministic environment. Non-deterministic environment. Here, single agent, we are talking about deterministic environment. In a deterministic environment, the solution will be a sequence. And what action, if I do, what will be the next state, that we know clearly. Okay, if I do this action, what will be the next state? That is known clearly. But that is not the case in games. Because in games, here games in the sense we are talking about multi-agent games. There are more than one player. If one player is trying to maximize his goal, the other player is trying to minimize his goal, that is the opponent's goal, right? So it is unpredictable opponent. In game, we have an unpredictable opponent. Always we have an unpredictable opponent, and we don't know what is the opponent is going to do. And according to the opponent's move, we have to make our move, so that it is called a strategic. That is specifying a move for every possible opponent reply. So depending on the opponent's move, we should make our plan. So we cannot make a plan only thinking of ourselves, right? We should also think of the opponent. If I do this, what opponent will do? If opponent will do that, then what should I do? Accordingly, we have to make a plan, right? And also there is a time limit. Time is another factor. Unlikely to find a goal must approximate. That what does it mean? It means that you don't have unlimited time. Within a specific time, you have to make the next move. Say for example, let us consider the chess with a timer. Chess with a timer. So there are two players, player one and player two. So if it is player one turn, player one will have some time. So player one should make the move within 5 minutes. Then within this 5 minutes, he has to identify the best move, right? So he does not have time to evaluate all the possible moves and find which is the best move. No. So there should be some approximation should be involved because your time is limited. So you cannot calculate everything perfectly. So you should allow the nature of the problem itself. It should allow for some approximation, right? So these are also some of the characteristics of games. So one is the opponent's move is unpredictable. As the opponent's move is unpredictable, that is, there may have multiple choices the opponent can make. Then accordingly, we should make a best choice. And also there is a factor of time limit. For every move, we cannot take unlimited time because our time is limited. So we cannot evaluate everything and then identify the best one and then make the move. No, we should do we should follow some form of approximation techniques, right? So this flowchart actually explains the concept of a two-player game, right? So in a two-player game, what happens? First, we are assuming that it is opponent's move. Let us assume it's not our move, it's opponent's move. So opponent makes some move. After making his move, he created a new position. The opponent has created a new position. Now this new position may be a game state, may be a goal state. So whatever the new position the opponent has created, it may be a goal. If it is a goal, then the game will over. So check whether it's a goal state or not. If it is a goal, then game is over. If game is over, then stop. If it is not over, if the game is not over, then it is our turn. Okay, this is opponent's turn. If the game is not over, then it is our turn. So we can make the move. Before making the move, what we do, we generate all the successes from the current state. This is the current state. From this state, what are the possible successors I can have? I can go to either this state, or I can go to this state, or I can go to this state, so on and so forth. These are the n possible states I can reach, right? Now evaluate all these n states. So which state? Now we should identify which is the good state. So apply some evaluation function and evaluate all these n states and identify some evaluation score. Say this E1 is the evaluation score of S1, E2 is the evaluation score of S2, E3, so on and so forth up to En. So we evaluate all the solution. Okay. After evaluating, then this is our current state. Then from the current state, we move to the state with the highest valued successor. All these are successors. Say out of this, whichever is the highest valued, say S3 is the highest valued, then we will move to S3. Then we'll move to S3. So now we have moved to a new state. Again, we check whether this is the goal state or not. If this is the goal state, then game is over. If game is over, then stop. If game is not over, then again it is opponent's turn. Now opponent will take his time. He will make the move, and this process continues. This process continues until the game gets over. So this is the overall scenario of a two-player game. Okay. So here our goal is to maximize our output, our successor, but the opponent's goal is to minimize our value, our point, right? Okay. So what we have discussed in the previous slide is, so this is the generic case. This is how generally the concept works. That is, at every state, generate all the successors, evaluate the successor, and move on to the one with the highest valued successor. But sometimes you may not have time to evaluate all the successors. Say we have to finish our move within 5 minutes, but say that we have 1,000 successors. Now you cannot generate all the successors and you cannot evaluate all the successors. In that case, we have to apply some approximation technique and we have to identify what will be the most appropriate move. Okay. So in most real world, it will be like this only, because we cannot create all successors always, and we cannot always evaluate all successors and find the next state, because we have a limit on the time, right? Okay. So games can be considered as adversarial search. Why we call it as adversarial search? Because always there is an opponent who is always trying to minimize our performance. As a player, we want to improve our performance. We want to maximize our performance. But there is an opponent who is always trying to minimize our performance. So when you consider the game as adversarial search, what are the things it involves? States. States are nothing but board configuration. If you take a chess game, then the different possible board configuration are the states. Initial state is the board position at which you are going to start. The present board position in which player will make a move. That is the initial position. Successor function is the set of operations that you can do. For example, if you take a chess game, what are the possible operations you can do? Where what is the rule of moving the pawn? How a pawn can be moved? How a rook can be moved? How a bishop can be moved? How a queen can be moved? All these are nothing but for for all operations we have to define an equivalent function. So all these are called a successor function. Returns a list of move state pairs. So if I make this move, then what will be the next state? If I make this move, what will be the next state? So basically, successor function, it returns a list of move state pairs, each indicating a legal move and the resulting state. Right. So what are the legal move that we know as per the rule of the game? How each, uh, I mean, how each coin can move, that we know, or that should be specified in the program. So successor function basically it returns a list of move and state pairs indicating the legal move and the resulting state. And the terminal test, it determines like whether the game is over or not, whether you have reached the goal state or not. And the utility function, it gives the numeric values in the terminal state. So based on this, when you apply the utility function on the terminal state in the sense here, the what you call the leaf nodes. The leaf nodes are nothing but the terminal states. So when you apply the utility function on the terminal state, you will understand what is the result, whether you have won or lost or it's a tie. So this is one example. Maybe at the terminal state, if you got a value of -1, it means you lost. If you got a value of 0, it means the game is tie. It is neither you or the opponent has win. If you got a value of +1, it means you won. Okay. So utility function basically it evaluates the terminal states and it says like whether the who has won the game. So here is an example of a two-player game in a deterministic environment. So before going to generally a game playing is a non-deterministic environment because you have two opponents and you don't know what the other opponent will move, what the other opponent choice will be, right? But still certain games can be considered as a deterministic game. So this example is for a deterministic game. So even there will be multiple states. There will be multiple states, but if you have sufficient time and sufficient computational power to analyze all the states, then it can be called as a deterministic problem. Okay. So this is one such example. So this is for a tic-tac-toe game. This is for a tic-tac-toe game. We are considering it as a deterministic environment, right? So the deterministic means what is the next possible move we know already, right? So here at every alternate turn, we call it as max min. So you can see this is max, this is min, max min, max min. It goes on like this. So we are trying to solve this from computer's perspective. We are trying to solve this from computer's perspective. So we are assuming ourselves to be computer and the opponent to be human, right? So we are considering ourselves to be computer and the opponent to be human. So whenever a computer's turn is there, the computer want to maximize. The computer want to maximize its result. Whenever it's opponent's turn, the opponent want to minimize the score of the computer. The opponent want to minimize the score of the computer. Okay. and the computer's move are represented using this symbol cross, and the opponent's move are represented using this symbol O. Okay, so first computer's move, which is called as max, because computer want to maximize his move. Then its opponent's turn, which is called as min, because opponent want to minimize the computer's move. Again it is computer's turn, compute, which is called as max, because computer want to maximize its product or output. Then it is opponent's move, opponent want to minimize computer's output, which is called as O. So on and so forth, it continues. So in a tic-tac-toe game, so the initially all the 9 blocks were empty. Okay, now the computer can make any one of these possible moves. This is the first possibility, this is the second possibility, this is the third possibility, so on and so forth. The computer can make any one of the 9 choices. In the first case, he can keep the first coin in the left corner, otherwise in the first row, second column, otherwise first row, third column, otherwise second row, first column, so on and so forth. So these are the 9 possible moves the computer can make during the first turn. Now as a result of this, these are the possible moves the opponent can make. If computer makes this move, then these are the possible moves the opponent can make. Already computer has made this move, that is it has kept the coin in the first row, first column. Now the opponent can keep its coin in the first row, second column, or first row, third column, okay, or second row, first column, or second row, second column, so on and so forth. If computer has made this move, if computer has made this move, then the opponent can make, he has 8 possibilities. He has 8 possibilities, right? So other than this position, the opponent can keep anywhere. Similarly, if the computer made this move, what are the possible moves of the opponent? Okay, fine, right? So next it will be computer's turn. Now for example, if originally computer made this move and opponent has made this move, now what move the computer can make? There are 7 possibilities. If originally computer made this move and opponent made this move, then what moves computer can make? Again there are 7 possibilities. So for each of these uh, 9 possibilities of computer, sorry, for each of these 9 possibilities of opponent, again the computer can make 8 different moves, right? The computer can make for sorry, so for each of these what do you call, for each of these, yeah, for each of these 8 different possibilities, the computer can make 7 different moves. The computer can make 7 different moves. Again it will be opponent turn. Now if these 3 are fixed, then the opponent can keep his coin in any of the remaining 6 positions. So for each of these 7 positions, the opponent can make 6 different moves, so on and so forth, it continues. So this process continues until it reaches the leaf nodes, until all blocks were filled. Okay, until all blocks were filled, or until, or somebody won, or somebody has already won. Okay, so this is one particular goal state. Here you can see it is -1, because who wants here? Here the opponent won. Here because opponent all zeros in one column he got, all O's. So opponent won, so computer failed, so it is -1. This is the case which is a tie. Nobody wins here. Neither the computer wins nor the opponent will. So this is a tie case. Whereas this, if you see here, the computer wins. So this x, you can see at a diagonal, all x were there. So this is +1. So this is a win by the computer. This is the win by the opponent. So whenever opponent wins, it is represented as -1. Whenever the computer wins, it is represented as +1. Okay. So see here, you should understand clearly from the root node, that is for the first, when computer makes the move, it has 9 possible moves, right? Now the opponent can make how many possible moves? For each of the 9 possible moves, the opponent can make 8 possible moves, right? So at this level you have 9 into 8. Are you getting? At this level, we have 9 into 8. Now, for each of these 9 into 8 possible moves, the opponent can make 7 different moves. So at this level, we have 9 into 8 into 7 possible moves. Okay. At the next level, for each of these 9 into 8 into 7 possible moves, okay, the computer can make how many moves? 6 moves. So 9 into 8 into 7 into 6. Right. Again, for each of the 9 into 8 into 7 into 6 moves, the opponent can make 5 different moves. 9 into 7 into 6 into 5. Right. So it goes on like this until it becomes 9 into 7 into 6 into 5 into 4 into 3 into 2 into 1. Okay. So which is nothing but 9 factorial. So if you see the total number of states, if you see the total number of states for this problem, for the tic-tac-toe problem is 9 factorial. Right. So if you have sufficient computing power, then you can explore all the 9 factorial states and you can make the best move in spite of the opponent is trying to minimize. Okay, so that we call this as deterministic. But as the problem increases, the number of states will increases and it will become more and more complex. Right? Even for this tic-tac-toe problem, we have the number of states as 9 factorial, so which is also a big number. Okay, so generally it's not deterministic because of the nature of the problem, because the state space is more, but we are trying to understand how the concept of game playing or how the concept of adversarial search works with an deterministic example. To understand, we are taking this deterministic example. Okay, right. So this strategy is called as minimax strategy. So this strategy, whatever we have discussed in the previous slide, this is called as minimax strategy. Why it is called as minimax strategy? Because at one round we are trying to maximize, and the other round the opponent is trying to minimize. Then the computer is trying to maximize. Then the opponent is trying to minimize the computer's performance. So it is called as minimax algorithm. It's a at one turn it is trying to minimize, and the other turn it is trying to maximize. Hence it is called as minimax algorithm. So in a minimax algorithm, a move, what we call as a move, when there is a move by both the players, then only we call as a move. That is, say for example, first the computer's turn, so it performs max. Then the opponent's turn, it performs min. These two things combinedly, it is called as a move. One max and one min, both put together, it is called as a move. Okay. So for example, there is next again computer makes a move. Again, opponent makes a move. Okay, that is opponent tries to minimize, computer tries to max. This is another move. So this is two moves. So totally now we have made two moves. Okay, and if we consider only computer makes a move or only opponent makes a move, that is called as ply. So a half move is called as a ply. Okay, so what is a full move? A full move is both when computer should also make a move and the opponent should also make a move, or both the players should make a move. Then only we will call it as move. If only one player makes a move, that is called as a half move, or that is called as a ply. Right? And the utility function is applied to the leaf nodes. So the utility function will help us to understand like what is the final value associated with that. And there is something called as backed up value. Right? So for a max position, that is if the player one is trying to maximize his position, then the backed up value will be the largest of its successor. Okay, for a min position, the backed up value will be the smallest of the successor. And not only this backed up value will propagate to the parent also. So things will be clear when we discuss an example for this. As of now, let us understand this much. For a max position, that is, if the player is trying to maximize his his score, then out of all his children, he will find the children with the maximum value. Okay, so the value of its largest successor is children. So for a max position, this will be the max of the children. This will be the max of the children if the node is trying to maximize. For a node which is trying to minimize, this will be the minimum of children. For a min position, the value of its smallest successor. Okay. But why we are calling as backup means, so this value will back up, it will go up to the parent, it will go up to the root node, right? So that when we discuss an example, the things will be clarified. Okay, right? So the min max procedure, what it does, it search down several levels. At the bottom level, that is at the leaf level, it will apply the utility function, and it will back up the values way up to the root node, and that node selects the move. So this is the generic way how it works. The search algorithm, actually it will go up to the bottommost level. So first it will be the max operation, then min. So max operation is by player one. Let us assume it is computer. Min operation is by the player two, that is opponent. Again max min, like that it will go up to the last node, that is the leaf node. On leaf node we apply utility function, and based on this utility function, the parent will get the value. So this is leaf node. Assume the parent of the leaf node is a max node. Okay, say there are, so this parent, say it has two child. Okay, one child is having value x, another child is having value y. Now if the parent is a max node, then it will get the maximum of these two values. Okay, so if y is maximum, then it will get y here. Then this is a, if this is a max node, then this is a min node. Then this node will get the minimum of all its children. If it has 5 children, out of all 5 children, what is the minimum value, that will go here. So on and so forth, this value will propagate up to the parent. So that concept is called as backing up. So that is how the minimax procedure works. Okay, so if you don't understand now fully, it's not an issue. When we discuss the, when we discuss an example, things will be clarified. But as of now, at the top level, you understand this much. When a move is done by both the players, player one also made a move for maximizing, and player two also has made a move for minimizing player one. So this both moves, this put together is called as a move. Okay, both actions put together is called as a move. If only one player made a move, then that is called as a ply or a half move. Then on the leaf node, we apply the utility function and we calculate the value, and the value will be backed up at the at the max position. The backed up value will be equal to the largest value of its successor. At the min position, the backed up value will be equal to the smallest value of its successor. And this min max algorithm, what it does, it it repetitively applies max min until it reaches the leaf node, and from the leaf node the values will be backing up to the parent. How it will back up, that depends on what parent it is, whether it is max or min. Okay. See, here is an example for min max, again under a deterministic environment. So with this algorithm, things will be, with this example, things will be clear. This is a two ply game. Two ply means what? Ply is a half move. When only one user makes a move, it is called as ply. So two ply means it is one move. So totally we have one move, that is one move by max, that is a half move by max, and another half move by min. Or player one makes a half move max move, and player two makes a min move. So this put together is called as one move or two ply. Okay. Right. So initially, say it is player one's move, that is player one want to maximize. So this maximize is represented using this triangle. Okay, using the triangle, and minimization is represented using the inverted triangle. Okay. So whenever it's maximizing, so the player one will always look for the child with maximum score. Here the score is given. Okay, so the player one has three successors. I mean, at this point, at the root node, when the player one is at root level, he has three successors: a1, a2, a3. a1 with the value of 3, a2 with the value of 2, a3 with the value of 2. So uh, so so the so the player one will choose what? Player one will always try to maximize. So he chooses his three, this three. That is, he's choosing this path. If player one chooses this path, now next is it is it is player two's turn. Player two always want to minimize player one's chance of winning. So given that player one has made this move, now what player two can do? Player two has three possibilities. Either it can allow this path, which will lead to 3, or it can allow this path, which will lead to 12, or it can allow this path, which will lead to 8. But player 2, what is objective? His objective is to minimize the score of player 1. So you don't want to maximize the score of player 1. So out of all these 3, it will take 3 only. It take the minimum one. Okay, because he want to minimize the output of player 1. So he will choose 3 here. Right? And this is the leaf node. Okay. So this is the case if player 1 chooses the first path. Obviously, player 1 chooses the first path only because player 1 always want to maximize. Right? But suppose, say that player 1 chooses the second path. If player 1 chooses the second path, then what player 2 will do? Then also player 2 will, out of this, which is the minimum 2, player 2 will choose this one. Okay. Suppose if player 2 chooses the third, player 1 chooses the third path, then out of these 3, which is the minimum one, 2. So player 2 will choose this one. Okay. But this 2 will not happen. Actually, player 1 will choose this path, and finally he will end up here. Right? Because this is the best thing that player 1 can do, nothing beyond that. Because there is an adversary, player 2 is the adversary who is always trying to minimize the performance of player 1. Okay, so here yeah, so this is a brief overview of the Minimax algorithm. We'll discuss one more example. With that, the backing up and the exact working of the algorithm will be clear. Right? So let us consider this tree. So initially, so these are the turns. So initially max, that is player 1 is going to play, who want to maximize his output. Then player 2 will play, who want to minimize player 1's performance. Then again player 2, again player 1. Okay. Say these are the leaf nodes. Let us assume that we know the value of leaf nodes. We know the value of leaf nodes. Okay. And the algorithm is something like it first goes this path fully. It is something similar to a depth first search. So so we go up to the leaf node. Okay, up to the leaf node we go. So we go to 84. First we go to this 84 node, right? The leaf node is what? 84. We come here, right? And this is what min. So min, say now only this is explode. This 84 only is explode. This 29 minus 29 is not explode. So out of 84, okay, this is min node. This is min node. Okay, he should choose minimum of his successor. But currently he has explored only this successor. Initially all these were 0. That is different. But now this 84 is explode. Okay, out of all the leaf nodes, this, say it is this 84 is explode. So what will come here? 84 will come here because only this is explode, so it will come here. Okay, for min, right? For max, so this is called as backing up. Let us try to understand what is backing up. See, at this point, all are zeros. If you see min, max, everything other than the leaf, everything is 0. But now the algorithm, the minimax algorithm, how it works in the sense, from the root, it will go up to the leaf level. The first it will take the leftmost path and it checks what is that 84. The leftmost node is 84. At the top, what is the parent? Parent is min or max? Min. So it will take the minimum of all the successor. But now we have explored only one successor, that is 84. So we know, as of now, we know only one successor, that is 84. So that value will go to the parent, because parent always wants the minimum value, and currently we have only one value, so it goes there, right? Now, so this is called as backing up. This 84 is now backed up to the parent. Now the backup will go to its parent also. Okay, but 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 what is the parent here? It is a maximize node, right? It is a maximize node. So what it will do? It will take the maximum of its two children. So when you compare 4 and okay, so this is a max node. It will check its two children, right? Only the leaf node we have not explored. Other nodes, let us assume it is explored. If it is red, I mean these green things were not explored. Okay, so out of this two, 84 and 0, what is the maximum? 0. So now we are backing up the 0 here, right? It continues again. The backup will go for the its parent also. Now this is minimize. It wants the minimum of 2. What is the minimum of this 2? Both are 0, so it is 0, and this will go to up to the root level. Here, what is the minimum of this 2? Again it is 0. Okay, so this is after 84. Now this is not its only child, it has another child also, minus 29. So now it has another child, minus 29. Now this is a minimizing player. So this player, he want to minimize. So he again compares this score 84 with minus 29. Which is the minimum? Minus 29 is minimum. So this will become minus 29. Okay, minus 29. So now it has backed up minus 29, right? Now this again this will be backing up. So here, but this is a max node. It want maximum of minus 29 and 0. So that is 0. This is minimum. It wants minimum of 0 and 0. That is 0. Again, this is maximum. It wants maximum of 0 and 0. That is 0. Okay. So now we have explored these two nodes. Now we have explored these two nodes, right? Okay. So similarly, the algorithm continues. So you can see here. So at this point, when you explore, when you finished exploring this two nodes, this point is minus 29. Okay, and here it is still 0 because this is a max node. When you compare this to 0 is the maximum. Okay, so now this is explored. So next the algorithm, it will go. So all these are explored. So it will come to this path. So now you find minus 37. So you find minus 37. This is not yet find. So again, this is a min node. So it has to find minimum of minimum. So it has only one choice, minus 37. So that will minus 37 will come here, right? Now what will be this max? Minus 29 and minus 37. What is the maximum of that? Minus 29 is the max. So here it will be minus 29. Okay, this is min. This is min. Okay, what is the minimum of minus 29 and 0? Minus 29 is the minimum. Okay, so minus 29 will come here. Again, what is the minimum of maximum of minus 29 and 0? So 0 will come here. Okay, so that is what next move after identifying minus 37. So that's what it is showing here. This diagram, if you see, after exploring minus 37 comes here, and here it is minus 29, because out of these two the max is minus 29. Here it is minus 29 because this is min. Out of these two the minimum is minus 29. Again, here it is 0 because out of these two the max is 0. Okay, so now we have explored only one child of this, but it has another child. So when you explore this child, what will happen? This is minus 25. Already this is minus 37. What is minimum? This player want to minimize. This is player 2 who always want to minimize the player 1's value. So minus 37 is the minimum one. So it will remain as minus 37. Okay, so there is no change because minus 37 is less than minus 25, right? So after exploring minus 25 also, here there is no change. Okay, so on and so forth, the algorithm continues. So now all these were explored. So now the algorithm will backtrack and it will explore this path. So when it explores this path, it is 1. Again, this is min. So when it comes here, it becomes 1, right? Out of then this, so this is called as backing up. So this value is backed up here. Again, it should be backed up. So out of, but this is a max node. Out of 1 and 0, which is max, 1 is max, so 1 will come here. Again, this is min. Out of minus 29 and 1, what is min? Minus 29 is min. Again, this is max. Out of minus 29 and 0, what is max? 0 is max. So that is what happened after exploring 1. Okay. So after exploring 1, this is here, it is not shown. Okay. So yeah, this is yeah, ideally it should be 1 here. Okay. I guess you understand. So after exploring 1, it should be 1, and so on and so forth. This should be 1. Yeah, only after exploring 1, this will be 1, because we don't know that minus 43. So out of this 2, this will be 0, so on and so forth. Okay. After exploring minus 43, what will happen? Previously it was 1 and minus 43, which is minimum minus 43. So minus 43 will come here. Okay. Then this is a max node. Okay. This is a max node. So out of I mean, yeah. So in the previous round also, this is also 1. Okay. Out of yes. So this is yes. Now we have explored both 1 and minus 43. So this is a min. Here we are doing min. So this becomes minus 43, right? Then in the next level, this is max. So minus 43 and 0, so it gets 0. Again, this is min. Minus 29 and 0, it gets minus 29. Again, it is max. Minus 29 and 0, it gets 0. Okay. So this is after exploring this path. So next we have to explore this path, right? So when you explore this path, again, what will happen? Yeah, first we explore only minus 75. So when you explore minus 75, so obviously this is min, so this becomes minus 75. This is max, minus 43 minus 75. So this will be minus 43. Okay. Again, this is min, minus 29 minus 43, minus 29 minus 43. So this will be minus 43, right? So because we explored only minus 75, this 49 we have not yet explored. So this minus 75 comes here. This is max. Max of this 2 is minus 43. This is min. Min of this 2 is minus 43. Okay. Max of minus 43 and 0 is 0. Right. So that's what it is showing here. It is minus 75. Here it is minus 43. Okay. Because this is the max of this 2. Here it is, again it is minus 43, because this is the min of this 2. This is 0, because out of 0 and minus 43, 0 is the max. Now when you explore 49, will there be any change? No change, because this will be minus 75 only, because this is what? Min. This is min. Okay. So after exploring 49, there is no change, because this wants the minimum one. It don't mind about that maximum thing, right? So now the entire left tree is explored. Similarly, we should do for the right subtree. Okay. Similarly, we should do for the right subtree. So we can do, so here directly it is shown. So for example, minus 29, minus 21. So first this will be minus 21. Okay. Then this is max, this is 0, right? Out of this 2, 0. Again, this is min, 0. Okay. Again, out of this 2, it is max, it is 0. But when you explore minus 51, which is minimum, minus 51 is minimum. So this becomes minus 51. Okay. After exploring this 2, this becomes minus 51. And max, this is again 0. Max of minus 51 and 0 is 0. Right. Min of 0 and 0 is 0. and max of 0 and minus 43 is 0. Okay, right? After exploring 58, this will become 58, right? Okay, and what is max of minus 51 and 58? This will be 58. Okay, what is min of 58 and 0? This will be 0. What is max of 58 and 0? It will be 0. After exploring minus 46, this will become minus 46 because that is the minimum, right? So this is max of minus 51 and minus 46. So which is max? Minus 46 is max. So this will become minus 46. Okay. This is what? This is min of minus 46 and 0. So this will become minus 46. Okay. This is max of minus 43 and minus 46. So this will become minus 43. Okay. This is after exploring 58 and minus 46. Then after exploring minus 3, this will become minus 3. This is max of minus 3 and 0 is 0. No change. And min of minus 46 and 0 is minus 46. And at the top, it remains the same. Okay. After exploring minus 13, this becomes minus 13 because this is minimum, right? Minimum is minus 13. So this becomes minus 13. Max of minus 39 and 0 is 0. So this remains 0. And min of minus 46 and 0 is minus 46. And max of minus 43 and minus and max of minus 43 and minus 46 is minus 43. Okay, fine. After exploring 26, this will become 26, right? And this is max of minus 13 and 26. So this will become 26. Okay, minus 13 and 26. This will become 26, right? Okay, and this is min of minus 46 and 26. So that will remain as minus 46. That will remain as minus 46. And this is max of minus 43 and minus 46. That will also remain as minus 43. And after exploring 79, there is no change because this is min. Anyway, it is going to pick up 26 only. So this is max of minus 13 and 26. That is 26. It is min of minus 46 and 26. That is minus 46. This is max of minus 43 and minus 43. That is minus 43. So this is what we get. So that is what is mentioned here. So you can see at the root we have minus 43, then minus 46. Okay, then minus 46 and 26, then minus 51, minus 46, yeah, minus 13 and 26, right? So like this, the tree is now fully explored. Okay, now you can identify what is the optimal path. So I'm optimal path from the perspective of player one. So we assume ourselves as player one. So what is the best thing player one can do? So what is the best thing player one can do? In the sense, for example, if assume that if player one makes the first move here, okay, if player one makes the first move here, right? So he will not make. Let us follow this. So player one always want to maximize. So minus 43, this is minus 43, this is minus 46. So what player one will do? He will make this move. Next, player two, this is player two's choice. Player two will try to minimize. So what player two will make a move? He want to minimize the chance of winning. Okay, so what player two will make move? Again, the player two will make this move, right? Okay, because player one wanted to maximize. So out of minus 43 and minus 46, the player one has chosen the highest number. Out of minus 43 and minus 46, minus 43 is the biggest number, so it came here, right? But player two want to minimize. Out of minus 29 and minus 43, minus 43 is the minimum value, so it moved here. Now again, it is player one's turn. Now player one want to maximize. So out of minus 43 and minus 75, he follows this path. He follows this path. Okay. Now again, it is player two. So player two want to always minimize. So out of this one and this thing, the player two will choose the one which leads to the least path, that is minus 43. Okay. So in this scenario, this is the best thing we can do. We cannot improve the solution further. Are you getting? Because there is an opponent. Because there is an opponent who is always trying to minimize our performance. Okay. So this is how min max works. So min max, so basically it is somehow, it is resemblance to an depth first search, but it is aware of an opponent, and according to the opponent strategy, it is making the move, right? Okay. So so this is the optimal move it can perform, right? Okay. So you may, why do we take the minimum value every other level of the tree? Because these nodes represents the opponent's choice of move. Okay. And we assume ourselves to be computer. That is, the player one is computer. The computer one always tries to maximize, whereas the opponent always tries to minimize. The computer assumes that the human will choose the move that is of least value. So P1 is the computer and P2 is human. Okay. P1 is computer and P2 is human. And we assume ourselves to be computer and we want to maximize our output. Whereas the human who is our opponent, he is trying to minimize our output, right? So that we are following this strategy at one time max and then min. So this algorithm is called as minimax algorithm, right? So this is the algorithm. This is a recursive version of the minimax algorithm. Here you can see minimax decision. This is the name of the algorithm. It takes a state and it returns an action. And what action, what path it should follow, that is given as max value of state. It just calls a function called max value of state. And what is max value? This is max value. This function, again, it's a separate function. It returns a utility value. Okay. If so, whatever the state the max value is receiving, if that is a terminal state, then return the utility of the state. Because only for the leaf node we have the utility. So if you recall the graph, if you recall the tree is something, it goes on like this. Okay, the previous tree which we have discussed. At the end, in the leaf nodes only we have some number, 43, 12, or minus 7, some numbers. These are the utility values. So that here we check whether it is whether the state is a terminal state or not. Terminal means leaf state. If that is the state, if that is a terminal state, then return the utility value, whatever the number associated with that, return. Otherwise, if that is not the terminal state, then we have to identify the value. Then we assume the initially the value to be minus infinity. In case of max, move, we assume the value to be minus infinity. Okay. Because max always tries to take the better value, right? He always tries to take a positive value, higher number. But as it is maximum, we are trying the least possible value. We are going to the negative infinity. Okay. Then for a comma s in successors of state, so you are passing some state to this algorithm, right? Let us assume it is a root state. Root state is passed to the algorithm. Then it says that you find for a comma s in successors of state do. That is, for all successors you do this operation. Let us assume the first successor is this. So for the first successor, what we are supposed to do? We are supposed to calculate this v equal to max of v comma min value of s. V equal to max of v comma min value of s. So s is the current state. S is the successor, first successor. So let us assume this is s1. Currently, let us assume s is equal to s1, the first successor. So max of v comma min comma value of s. So previously, what is v minus infinity? So it is saying that you find max of minus infinity comma the minimum value of yes. Okay, because in the next round it should go for min, right? So what is this min? Again, it is another function, it is defined here, right? So min value of state returns a utility value. Again, we are checking if it is a terminal state, then return the utility state. Otherwise, we set v equal to infinity, because min will take always minimum value. So here we are checking, setting it as high positive number, which is infinity. Then again, here you see what we are doing. Again for this we are creating successor. So this state is paused, this s1 is paused here. For this we are creating all the successor, right? So it has many successor. Let us assume its first successor is called as s11, and now that we are calling as s for a comma s in successor of state. So this is s1 at this point, this is s. Okay, but the successor of s1 is say s11, s12, all these things are, this is s12. We are taking s11. Let us assume s11 is yes. Then again what we do, v is equal to min of, so here we say v is equal to min of v. What is v now? Infinity. Infinity comma max value of yes. So again this function calls this function, again this function calls this function. So it is one function calling another function. See this, are you getting? This max is calling this min, and this min is calling max. It is calling like this repetitively, right? So this node is passed again as a parameter to max, right? And it will create all its children. How long it continues? Until it reaches the leaf node, right? At one point it will reach the leaf node, and then it will return the utility. So whatever the utility, it will go to the parent. Okay, say it has reached the leaf node, so that utility value will go to the parent. So if its utility value is 42, this 42 will come here. Now min of infinity and 42 is what? Positive infinity and 42. What is minimum? 42 is minimum, so it will take 42. Okay, it will take temporarily 42, but this is not its only child, it has another child also. Then this loop will repeat for one more time. Are you getting? So next time when it returns, it will return 12. So now it is min of 42 comma 12. So basically it will take 12 because that is the minimum. Okay, next it will, this 12 will be returned to this max, because at the top we have max, so 12 will come here. But this is not its only child, it may have another child. So in that path also, okay, so in that path it may have some children. So based on that it will get the minimum value, and that maximum value again come. Are you getting? So there it will say, here it will be max of first round minus infinity comma 12, out of minus infinity 12, which is bigger 12, right? So temporarily it will take 12, but that is not its only child, it has another it may have another child also, it may explore, but there it will perform in so on and so forth. So like that, this is it calls the max calls the min, and min calls the max. It goes on until it reaches the leaf node, and finally whatever the algorithm we have discussed previously, this whatever the steps we have discussed, that is actually clearly will be done by this coding, right? So that's what it does. So further you can explore this algorithm by yourself. I have given a glimpse on that, the working procedure. Okay. Fine. So now let us try to analyze the properties of minimax algorithm, right? Whether is it complete? So basically it is something like a DFS. So most of the properties of DFS actually is applicable to minimax. So it is complete if the tree is finite. So that is the case with DFS also. DFS is complete in a finite state space. So it is complete in a finite state space. Is it optimal? DFS is not optimal, but this is optimal. Minimax is optimal against an optimal opponent, right? See, in this example, we have identified an optimal solution against an optimal opponent. So we assumed our opponent also to be optimally optimally competitive like us. So then we are able to identify this optimal solution. So with an optimal opponent, minimax is optimal. Okay, because when an optimal opponent is working, this is the best solution you can arrive at. There is no other best solution. So is it optimal? Yes, it is optimal against an optimal opponent. But if the opponent is not optimal, then it is not optimal. Okay, if the opponent is not optimal, it is not optimal, right? That means that if the opponent is suboptimal means opponent is not playing with his full potential. Okay, then actually this algorithm cannot exploit the weakness of the opponent. It cannot exploit the weakness of the opponent, and it cannot improve the result further. So you getting? See, normally in a game, two player game, in any game, okay, if both or if both are both the players are very talented, okay, then what you then the chance of winning is very less, right? For both of them, it, it will be a tough game. Okay, but if one of the player is suboptimal, then the other player can exploit his weakness. Then the other player can exploit his weakness, right? But actually that doesn't happen in minimax algorithm. If the opponent is optimal, then it will identify the optimal solution. I mean, it's not here optimal in the sense it's not the best solution. Given the opponent's what you call opposition, given the opponent's full opposition in place, it will find a optimal solution. Okay, but if the opponent is suboptimal, then it cannot exploit the weakness of the opponent, and it cannot perform better. So in that context, if the opponent is not optimal, it is the algorithm is not optimal. Okay, its time complexity is same as that of depth first search, order of b to the power m, and its space complexity is again order of depth same as that of depth first search. It is order of bm, right? Okay, so this is the brief introduction to minimax algorithm and adversarial search. So let us stop here for today's discussion. Thank you.